Have you ever gazed up at the night sky and wondered if we are truly alone in the universe? That question has haunted humanity for centuries, sparking our imagination and driving our curiosity to explore the cosmos. And now, with incredible advancements in science and technology, we stand on the brink of answering that age-old mystery. Telescopes and space missions have already discovered thousands of planets beyond our solar system, and among these distant worlds, a select few show signs that they could support life as we know it. It's a thrilling time to be alive, because every new discovery brings us closer to finding another living world, and possibly another civilization. Today, we embark on an extraordinary journey to 25 alien worlds that could harbor life. Picture swirling oceans under alien suns, skies tinged with colors we've never seen, and landscapes that defy our wildest dreams. These aren't just points of light in a telescope. They are real places with real potential. From scorching hot super-Earths to icy moons with hidden oceans, each of these exoplanets offers a unique environment where life might have taken hold. We'll explore what makes these worlds so special, what conditions scientists are looking for, and why the search for extraterrestrial life is one of the most exciting quests in modern science. This video is your ticket to adventure, a chance to travel across light years without leaving your seat. We'll uncover the latest research, break down complex astronomy into easy-to-understand ideas, and imagine what life might look like on these distant shores. Whether you're a seasoned space enthusiast or just curious about the universe, there's something here to ignite your sense of wonder. So sit back, open your mind, and let's set course for the unknown, because the answers are out there waiting to be discovered. Our journey begins right next door, cosmically speaking, with a world so close its star is visible to the naked eye. Just 4.2 light-years away, orbiting the small, red dwarf star Proxima Centauri, is Proxima Centauri b. This isn't a distant, theoretical point of light. This is our immediate interstellar neighbor, a planet with a mass remarkably similar to Earth's, sitting snugly within its star's habitable zone. This is the region around a star where conditions are just right, not too hot, not too cold, for liquid water to potentially exist on a planet's surface. And where there is liquid water, as we know from our own world, there is the tantalizing possibility of life. But Proxima Centauri b is a world of stark contrasts and formidable challenges. Its host star, Proxima Centauri, is a far cry from our steady, benevolent sun. It's a tempestuous red dwarf, prone to violent outbursts of radiation called stellar flares. These eruptions can be hundreds of times more powerful than anything our sun produces, bombarding the planet's atmosphere and surface with intense X-rays and ultraviolet radiation. For life as we know it, this is a harsh environment, a constant barrage that could strip away a protective atmosphere or prevent life from gaining a foothold in the first place. Adding to the complexity is the planet's likely state of tidal locking. Because it orbits so close to its dim star to stay warm, completing a full year in just 11 Earth days, gravitational forces have probably caused the same side of the planet to permanently face the star. This creates a world divided into two eternal realms. One hemisphere is locked in perpetual daylight, a scorching landscape under a constant, dull red sun. The opposite hemisphere is trapped in an endless, frigid night. The most likely region for habitable conditions would be in the slim, temperate twilight zone along the Terminator line, where day meets night. Here, in this band of eternal sunset or sunrise, temperatures might be moderate enough for liquid water to pool on the surface or exist in subsurface reservoirs. Despite these extreme conditions, the potential for life cannot be ruled out. Life on Earth has proven to be incredibly resilient, thriving in the most unexpected places, deep in ocean trenches, buried under Antarctic ice, and in boiling acidic springs. If Proxima Centauri b managed to retain a thick atmosphere, It could theoretically redistribute heat from the day side to the night side, creating more temperate conditions across the globe. Its oceans, if they exist, could harbor ecosystems shielded from the stellar fury above. This nearby world serves as a powerful reminder that habitability is not about being an exact copy of Earth, but about possessing the right ingredients and circumstances for chemistry to become biology, even under an alien sun. While our nearest neighbor offers a tantalizing possibility, the search for life extends far beyond a single star. A mere 40 light-years away lies a stellar system that has captivated astronomers like no other, TRAPPIST-1. This ultra-cool red dwarf star is home to a breathtaking family of not one or two, but 7 known Earth-sized planets, all orbiting closer to their star than Mercury does to our Sun. It's a compact, bustling solar system that feels almost engineered for discovery. And of these 7 siblings, one world stands out as a prime candidate in the hunt for life, TRAPPIST-1e. What makes this particular planet so compelling is its striking Earth-like profile. TRAPPIST-1e is almost identical in size to our own world and has a very similar density, strongly suggesting a rocky composition with a solid surface you could theoretically stand on. Its orbit is perfectly situated within the star's habitable zone, that Goldilocks region where temperatures could be just right for liquid water to pool and flow. But in the TRAPPIST-1 system, the habitable zone isn't a lonely place, it's a shared neighborhood. TRAPPIST-1e is one of 3 planets in this coveted orbital real estate, meaning if life can arise here, it might not be alone in its own solar system. The potential environments on this world are a subject of intense speculation and scientific modeling. Some calculations suggest TRAPPIST-1e could possess a thick, insulating atmosphere, perhaps similar to Earth's, which would be crucial for maintaining stable, temperate climates and protecting the surface from the star's radiation. Other models raise the possibility of a global ocean, a true water world with no land in sight, its entire surface a deep, alien sea. The climate on such a world would be profoundly shaped by its proximity to its star and its siblings. Imagine a sky where the other planets appear as large as our moon, or even larger, creating a spectacular, ever-changing celestial dance visible during both day and night. The true excitement around TRAPPIST-1e lies in its testability. The system's alignment from our vantage point is ideal as the planets regularly transit or pass in front of their star. Each time this happens, a tiny fraction of the star's light filters through the planet's atmosphere if it has one. Our powerful telescopes, like the James Webb Space Telescope, are designed to analyze this filtered starlight, looking for the chemical fingerprints of potential life. These biosignatures could include gases like oxygen, which on Earth is largely produced by life, or methane, which can be a byproduct of biological processes. Finding a mix of these gases in the atmosphere of TRAPPIST-1e would be one of the most significant hints that we are not alone in the universe. This world represents not just a point of light, but a tangible, reachable target in our quest to find another living planet. While TRAPPIST-1e shows us the potential of a crowded stellar neighborhood, our next destination represents a historic milestone all on its own. Traveling nearly 500 light-years into the constellation Cygnus, we find Kepler-186f, a world that forever changed our perspective on the cosmos. Discovered by the Kepler Space Telescope in 2014, this planet earned a monumental title, the very first Earth-sized world ever confirmed to be orbiting comfortably within the habitable zone of another star. Before this discovery, we knew of larger, super-Earths in these life-friendly regions, but finding a planet so similar in size to our own was a game-changer, providing the first solid evidence that planets like ours are not rare quirks of our solar system, but could be common throughout the galaxy. Kepler-186f orbits a red dwarf star, much like Proxima Centauri b and the TRAPPIST-1 planets, but its orbit tells a different story. It completes a journey around its star every 130 days, placing it significantly farther out than many of its counterparts. This greater distance is crucial because it likely shields the planet from the most violent effects of stellar flares. While its star is still active, the increased orbital distance means Kepler-186 might not be tidally locked, potentially spinning on its axis much like Earth does. This rotation would create a familiar cycle of day and night, allowing for more even distribution of heat across the globe, and preventing one side from being perpetually baked while the other freezes. This single characteristic moves it significantly higher on the list of potentially habitable worlds. Theories about its composition are equally fascinating. Based on its size, which is just 10% larger than Earth's, scientists are confident it is a rocky planet with a solid surface. Its density suggests it could have a similar internal structure, with a metallic core and a rocky mantle. This opens the door to one of the most exciting possibilities: plate tectonics. On Earth, the slow movement of continental plates is vital for regulating our climate by recycling carbon dioxide over long timescales. If Kepler-186 has active tectonics, it could be a powerful stabilizing force, maintaining a temperate climate that is conducive to liquid water and, potentially, life for billions of years. This leads to the captivating question of what its surface might actually look like. Could Kepler-186 have its own versions of continents and oceans? With a size and position so reminiscent of Earth, it is a compelling possibility. Computer models suggest it has likely retained a substantial atmosphere, which would be essential for maintaining surface pressure and temperature. We can imagine a world with vast, deep blue oceans under a pinkish sky, lit by a star that appears only half as bright as our Sun, but shines with a distinctive orange-red hue. The land masses, if they exist, could be familiar yet utterly alien, shaped by forces of erosion and geology we would recognize, but composed of minerals we have never seen. Kepler-186 stands as a quiet pioneer, the first proof that planets with the right size and the right location are out there, waiting for us to learn their secrets. Moving from the historic discovery of Kepler-186 we venture just 40 light-years away to another red dwarf system, where a dense and mysterious super-Earth commands our attention. LHS 1140b isn't just another exoplanet. It's a heavyweight champion in the category of potentially habitable worlds, a planet whose very construction hints at incredible possibilities. Discovered in 2017, this world orbits a star that is both calmer and older than Proxima Centauri, offering a potentially more stable environment for life to arise over billions of years. What truly sets LHS 1140b apart is its extraordinary density. While it's about 1.7 times the size of Earth, its mass is a staggering 6.5 times greater. This means the planet is incredibly dense, a characteristic that points overwhelmingly toward a rocky, metallic composition, a true super-Earth. This isn't a puffy gas mini-Neptune. All indications are that this is a solid world with a defined surface, likely featuring a massive iron core and a robust rocky mantle. That substantial mass has a major advantage. It would provide enough gravity to hold onto a significant atmosphere, a critical shield against stellar radiation, and a key ingredient for maintaining liquid water on the surface. Its orbit places it squarely in the middle of its star's habitable zone, but its journey around its calm red sun is remarkably short, just 25 Earth days. Because the star is so dim and cool, this close orbit is necessary to receive enough warmth for liquid water. The stability of the parent star is a huge point in this planet's favor. Unlike the flare-prone Proxima Centauri, LHS 1140 is a quiet, mature star, which means its planet has been basked in a relatively gentle and constant light for billions of years. This long, peaceful period is exactly the kind of extended stability that, on Earth, allowed life to not only emerge but to evolve and thrive. The most exciting chapter for LHS 1140b is being written right now by the James Webb Space Telescope. Its primary mission is to determine if this dense world has managed to retain that thick atmosphere we suspect it could hold. Scientists are eagerly analyzing the starlight that filters through the planet's air during its transits, searching for the telltale chemical signatures of gases like nitrogen, carbon dioxide, water vapor, or even methane and oxygen. The presence of the right combination of these gases could transform this exoplanet from a promising candidate into a frontrunner for hosting life. Given its probable conditions, one compelling theory suggests LHS 1140b could be a vast, eyeball planet, with a massive ice cap on its perpetually dark side if it is tidally locked, but a giant liquid ocean directly under its star. An even more captivating idea is that it could be a completely covered water world, a global ocean hundreds of kilometers deep, hiding secrets in its abyssal darkness. The high pressure at the bottom of such an ocean could create a layer of exotic ice, but nearer the surface, where sunlight penetrates, conditions might be perfect for aquatic life to develop. This world represents the next step in our search, not just finding planets in the right place, but using our most advanced tools to sniff out the air they breathe, bringing us closer than ever to answering the ultimate question. Shifting our gaze 100 light-years away, we encounter a discovery that perfectly illustrates the power of modern planet-hunting missions. In the constellation Dorado, the Transiting Exoplanet Survey Satellite, or TESS, spotted a world that immediately captured the attention of astronomers everywhere, TOI 700d. This planet holds the distinguished title of being the first Earth-sized world found by TESS orbiting within the habitable zone of its star, a discovery that validated the satellite's incredible potential to expand our catalog of life-friendly worlds. What makes TOI 700d such a compelling candidate begins with its parent star. Unlike many of the volatile red dwarfs we've discussed, TOI 700 is an exceptionally quiet M-dwarf. It shows little sign of the violent stellar flares that so often threaten the atmospheres of planets orbiting its stellar cousins. This prolonged calm is a gift for any potential biosphere, offering a stable, predictable environment where life could develop over eons without being periodically scorched by intense radiation. The planet itself completes an orbit every 37 days, a year that feels incredibly short to us, but is perfectly normal in the cooler embrace of its dim star. The true wonder of this world lies in the climate models scientists have built. Using sophisticated computer simulations, researchers have explored a range of plausible atmospheres and surface conditions for TOI 700d. One of the most tantalizing scenarios suggests it could be a water world, completely enveloped by a deep, global ocean beneath a thick, cloud-filled atmosphere. In this model, the skies would be constantly overcast, with frequent rainfall nurturing a planet-wide sea. Another compelling model paints a very different picture, a world with a significant landmass, a vast supercontinent perhaps, with clouds gathering over its sun-facing side and prevailing winds carrying moisture across the terrain. In this version, it could look surprisingly familiar, a place with recognizable weather patterns dancing above an alien landscape. The significance of its discovery cannot be overstated. Before TESS began its survey, we weren't certain how many stars like TOI 700 would host planets of this size and position. Finding one so early in the mission was a tremendous boost, proving that such worlds are out there and within reach of our instruments. It serves as a perfect example of a world we can study in depth with the James Webb Space Telescope. Its quiet star and clear transits make it an ideal laboratory for atmospheric spectroscopy, the process of dissecting starlight that passes through its air to identify its chemical composition. We could soon know if its skies contain water vapor, carbon dioxide, or even the elusive molecular oxygen that often hints at biological activity. TOI 700d isn't just a pinprick of light. It's a promise of future discovery, a nearby world holding its secrets just out of view, waiting for our technology to reveal them. Our journey now takes us over 1,000 light-years from Earth to a pair of worlds discovered by the Kepler Space Telescope, each offering a unique and compelling vision of what an Earth-like planet might truly be. The first of this duo, Kepler 442b, is a world that scores extraordinarily high on a scientific scale known as the Earth Similarity Index. This index measures how closely a planet's physical properties, its size, density, and the energy it receives from its star, match those of our own world. Kepler 442b isn't just similar. It's one of the most Earth-like exoplanets we've ever found. A rocky world about 1/3 larger than Earth, orbiting comfortably within the habitable zone of its orange K-dwarf star. What truly sets this planet apart is the quality of light it receives. Its star is cooler and redder than our Sun, but Kepler 442b orbits at a distance where the flux of stellar energy hitting its atmosphere is remarkably similar to what Earth receives. This opens up a breathtaking possibility that goes beyond mere liquid water: the potential for photosynthesis. On Earth, this process is the foundation of almost the entire biosphere, allowing plants to convert sunlight into chemical energy. The light from its K-type star, rich in the red and infrared wavelengths, could potentially be harnessed by alien plant life. We can imagine a landscape where any vegetation has adapted to this dimmer, redder sun, perhaps sporting leaves of deep black or purple to absorb every available photon, creating an ecosystem fundamentally familiar yet visually alien. While Kepler 442b presents a vision of life under an alien sun, its sibling discovery, Kepler 452b, feels hauntingly familiar. Orbiting a G2-type star, the same classification as our own Sun, this planet earned the nickname Earth's cousin for very good reasons. Its star is almost a twin to the Sun in terms of temperature and size, and it's only about 20% brighter and 1.5 billion years older. This means the Kepler 452 system is like a glimpse into a slightly more mature version of our own solar neighborhood, offering a preview of what might lie in Earth's distant future. The planet itself completes one orbit every 385 days, a year just 20 days longer than our own. It spends that year firmly within its Sun-like star's habitable zone, basking in an amount of sunlight only about 10% greater than what Earth receives. This combination of a familiar star and a familiar orbital period makes it one of the most psychologically compelling exoplanets we know of. The potential for habitability here is profound. With a diameter 60% larger than Earth's, it likely falls into the category of a super-Earth, possessing enough gravity to hold onto a substantial atmosphere and possibly even maintain plate tectonics due to its presumed rocky composition. The older age of the system is particularly intriguing, as it has had an extra 1.5 billion years for the chemistry of life to arise and evolve into complex forms, should the conditions be right. Together, these two worlds represent different pathways to potential habitability. Kepler 442b shows us that a planet doesn't need a sun-like star to be a strong candidate. It can thrive under a different, cooler sun and still possess the right conditions for life, perhaps even developing its own unique photosynthetic processes. Kepler 452b, on the other hand, demonstrates that there are systems out there that mirror our own with stunning accuracy, worlds that orbit a similar star on a similar schedule, suggesting that if the recipe for Earth worked here, it could very well have worked there too. They stand as powerful reminders that Earth might not be a singular miracle, but one variation on a theme of habitable worlds that the universe seems to compose with astonishing frequency. But the universe doesn't only build planets around single stars. Sometimes it creates celestial wonders in systems of incredible complexity. That's precisely the case for our next world, JWST, a planet that dances in the light of not one, not two, but 3 suns. This super-Earth is part of a triple star system located a mere 22 light-years away, making it one of our closest interstellar neighbors. While its primary parent is a small, cool M dwarf, the other two stars in the system are themselves a binary pair of K dwarfs orbiting farther out. From the planet's surface, you might see one large, dull red sun in the sky, with two much brighter and distinctly orange companions visible during their day. A truly alien sunset that would put Tatooine to shame. What makes JJ667 so intriguing is its mass, which is remarkably similar to Earth's, suggesting a rocky composition we would find familiar. It orbits snugly within the habitable zone of its primary star, completing a full revolution in just 28 Earth days. The presence of multiple stars adds a fascinating layer to its potential climate. While the two distant K dwarfs provide only a small amount of additional heat, their gravitational influence and light could create subtle yet complex effects on the planet's atmosphere and seasons. The real hope for this world lies in its ability to retain a thick atmosphere. If it possesses a significant blanket of air, that atmosphere could effectively trap the star's feeble heat, distributing warmth across the globe and potentially raising surface temperatures to levels that allow for liquid water. This scenario turns a world that might otherwise be an ice ball into a candidate for habitability, proving that even in a crowded stellar neighborhood, the right conditions can arise. The most astonishing revelation in the search for habitable worlds recently came from a planet known as K218b. Located 120 light-years away in the constellation Leo. This isn't just another super-Earth in the habitable zone. This is a world where we have already detected the unmistakable signature of water vapor in its atmosphere. That discovery, made by the Hubble Space Telescope, catapulted K218b into a league of its own. It was a landmark moment, the first time we had identified water vapor in the atmosphere of a habitable zone exoplanet, a crucial piece of the puzzle we had been searching for. K218b is significantly larger than Earth, with a radius about 2.6 times greater, placing it in a category between a rocky super-Earth and a mini Neptune. This size means its composition was initially a mystery. However, the detection of water vapor, along with a hydrogen-rich atmosphere, points towards a unique and fascinating structure. Scientists now believe it may be a Hycean world, a theoretical planet type with a massive global ocean covering its entire surface, beneath a thick, hydrogen-dominated atmosphere. On such a world, there would be no land. The entire surface would be a water world, with ocean depths potentially reaching hundreds of kilometers. The pressure at the bottom of such an abyss would be crushing, possibly forming a layer of exotic high-pressure ice. But nearer the surface, where starlight can penetrate, conditions could be far more temperate. This hydrogen-rich atmosphere, while very different from our own nitrogen-oxygen mix, is not necessarily a deal-breaker for life. In fact, it could act as a powerful greenhouse blanket, keeping the planet warm enough for its global ocean to remain liquid despite orbiting a cool red dwarf star. The presence of water vapor confirms that this world has one of the three essential ingredients for life as we know it. The next step, eagerly awaited, is for the James Webb Space Telescope to train its powerful instruments on K218b. Its mission will be to look for other molecules in that atmosphere, specifically biomarkers like dimethyl sulfide, which on Earth is only produced by living organisms. Finding such a sign would be a profound step toward confirming that we are not alone, suggesting that life can not only exist on planets like our own, but also thrive in the deep, dark oceans of an alien waterworld. While many of the worlds we've visited orbit stars visible to the naked eye, our next destination circles a sun so faint it wasn't even discovered until 2003. Just 12 light-years away, Teegarden's star is an ancient red dwarf, a stellar ember so dim and cool that despite its proximity, you would need a powerful telescope just to see it. Yet around this cosmic ghost, Astronomers found not one, but two planets, and the inner world, Teegarden Star B, immediately stunned the scientific community by achieving the highest Earth Similarity Index score ever recorded. That means, on paper, this world is the most Earth-like exoplanet we know of in terms of its size and the energy it receives from its star. What makes this so remarkable is the delicate balance at play. Teegarden Star is exceptionally cold and dark, emitting most of its energy as infrared radiation. For the planet to be warm enough for liquid water, it must orbit incredibly close, completing its entire year in just 4.9 Earth days. At that distance, you might expect the planet to be roasted, but because the star is so feeble, this tight orbit actually places it perfectly within the habitable zone. The sunlight reaching its surface would be wan and reddish, a perpetual twilight glow that provides just enough energy to potentially keep water in its liquid state, while also posing a profound question about the nature of its atmosphere. The true enigma of Teegarden Star B is the mystery of its air. The planet has a minimum mass almost identical to Earth's, suggesting a solid, rocky world. But could such a planet, orbiting so close to its star, even a quiet one, hold onto a life-sustaining atmosphere over billions of years? Some models are optimistic, indicating that with a protective magnetic field or a sufficiently dense mixture of greenhouse gases like carbon dioxide, it could maintain a stable climate. This atmosphere would be crucial for distributing what little heat it receives from its star, preventing the world from becoming a frozen ice ball or a scorched rock. This leads to a captivating vision of what life might look like in such a low-energy environment. Any potential biology would have to adapt to a world of deep reds and near darkness. Photosynthesis, if it exists, would be wildly different from our own, likely optimized to capture every possible photon of infrared light. Imagine vast forests of black or deep crimson vegetation carpeting the landscape, their leaves designed to absorb every last bit of energy from the dim sun. Animal life, in turn, might develop highly sensitive eyes or evolve to use other senses entirely, like sonar or sensitivity to magnetic fields, to navigate their perpetually twilight world. Teegarden's Star B stands as a silent testament to the universe's creativity, a world that matches our own in key metrics while offering an environment so alien that it challenges our very definition of what it means to be habitable. Venturing just 14 light-years from our solar system, we find a system that feels almost within reach, a neighbor with a world that challenges our understanding of planetary stability. Wolf 1061c is a super-Earth, a rocky planet about 1.8 times the mass of our own world, and it orbits squarely within the habitable zone of its M-type red dwarf star. Its discovery was significant not just for its potential to host life, but for its astonishing proximity to us. At a mere 14 light-years away, it is one of the closest known potentially habitable exoplanets, a stone's throw away in galactic terms. The parent star, Wolf 1061, offers a mixed blessing. It is quieter and more stable than many of its volatile red dwarf cousins, which is a huge advantage for fostering a stable climate over billions of years. However, the planet's orbit is exceptionally tight, completing a full revolution around its dim sun in just 18 Earth days. This close relationship likely means the planet is tidally locked, with one hemisphere perpetually bathed in faint reddish light, and the other plunged into eternal darkness. The most likely haven for life would be the thin, ribbon-like terminator zone between these two extremes, a land of perpetual sunrise or sunset where temperatures might be moderate enough for liquid water to exist. The most fascinating and potentially challenging aspect of Wolf 1061c involves its orbital eccentricity. Unlike Earth's nearly circular path around the Sun, this world may travel on a slightly elliptical or oval-shaped orbit. This subtle difference could have dramatic consequences, creating what scientists call climate oscillation. As the planet moves closer to its star during its year, it would experience a period of intense warming, a kind of infernal summer. As it swings farther away, it would plunge into a deep, global freeze. This constant, radical shifting between extreme heat and extreme cold could make it incredibly difficult for life to establish a foothold, as any budding ecosystem would be regularly reset by these climatic convulsions. Yet, nature is resilient, and this very instability could also be a driver for adaptation. Some astrobiologists speculate that if this world possesses a global ocean beneath a thick atmosphere, the vast body of water could act as a climate buffer, absorbing heat during the warm phase and releasing it during the cold, moderating these wild temperature swings. Life could potentially thrive in such an ocean, protected from the chaotic changes on the surface. With its location so tantalizingly close, Wolf 1061c is a prime target for the next generation of telescopes, which will aim to settle these debates by directly analyzing its atmosphere for signs of water vapor, carbon dioxide, and other gases that would reveal the true nature of this nearby, turbulent world. The search for a second Earth sometimes feels like looking for a needle in a cosmic haystack, but every so often, we find a glimmer that stops us in our tracks. That's precisely what happened when astronomers, sifting through old data from the retired Kepler Space Telescope, discovered a world that had been hiding in plain sight. Kepler 1649c isn't just another exoplanet. It's a remarkable reminder of the treasures still buried in archived data, and it stands as one of the most Earth-like worlds we've ever found. What makes this discovery so extraordinary are the numbers. Kepler 1649c is almost exactly the same size as our own planet, with a radius just 1.06 times that of Earth. This strongly suggests a rocky composition, a world with a solid surface where you could theoretically stand. But the similarities don't end there. This planet orbits within the habitable zone of its cool, red M-dwarf star, receiving about 75% of the stellar energy that Earth gets from the Sun. To put that in perspective, if you could swap Earth and Kepler 1649c, our world would freeze over into a global ice ball. But for a planet already adapted to a dimmer sun, this energy level is perfect, placing it in the ideal temperature range for liquid water to exist on its surface. This combination of Earth-like size and Earth-like stellar energy receipt is incredibly rare. Out of all the thousands of exoplanets discovered by Kepler, this one has the most similar combination of these two key factors. It's like finding a planet that checks the two biggest boxes on our habitability list. Its orbit is another point of fascination. It completes a year in just 19.5 Earth days, and it's tidally locked to its star, meaning one side is in constant daylight while the other is in endless night. The most habitable region would likely be the line of twilight that separates these two extreme hemispheres, a place where temperatures could be just right. To truly appreciate its potential, it's helpful to compare it to our solar system neighbors. Imagine a spectrum with Venus on one end and Earth on the other. Venus, with its thick, crushing carbon dioxide atmosphere and runaway greenhouse effect, is a scorching hellscape. Earth, with its protective atmosphere and temperate climate, is a life-giving oasis. Kepler 1649c appears to fall much closer to our own world on that spectrum. It receives significantly less energy from its star than Venus does, making a runaway greenhouse scenario far less likely. Instead, its conditions seem to mirror what we might find on a slightly cooler version of Earth. The parent star, however, adds a layer of complexity to this promising picture. It is a red dwarf, and like many of its kind, it is prone to flares, sudden, violent eruptions of radiation that can bombard nearby planets. Without a protective magnetic field or a robust atmosphere, such flares could strip away any chance for life. Yet, the very existence of this planet gives us hope. Its discovery proves that planets with the right size and the right location exist around even the most common stars in the galaxy. Kepler 1649c is more than just a data point. It is a symbol of possibility, a nearby mirror reflecting our own world's image and urging us to keep looking. Leaving the realm of dim red dwarfs behind, we now journey to a star that feels a bit more like home. 44 light-years away in the constellation Pictor, the orange dwarf star HD 40307 shines with a warm, familiar glow. This star is a kind of cosmic middle child, not as large and hot as our Sun, but not as small and cool as the red dwarfs that dominate our list. And orbiting this star is a world that captured attention for its promising location, the super-Earth known as HD 40307G. What makes this planet so compelling is its orbit. Unlike the incredibly short years we've seen on many other worlds, a single orbit here lasts just under 200 Earth days. This places it firmly within the star's extended habitable zone, a region where the energy received is just right for liquid water. Because the parent star is an orange K-type dwarf, it is more stable and less prone to violent flaring than its smaller M-dwarf cousins. This offers the planet a far more serene and consistent environment, one that could be conducive to life developing over billions of years without the constant threat of stellar tantrums. As a super-Earth with a mass several times greater than our own world, HD 40307G likely possesses the gravitational strength to hold onto a massive, thick atmosphere. This atmospheric blanket would be its key to life. Sophisticated climate models have been run on this planet, and the results are incredibly encouraging. They suggest that with an atmosphere similar to Earth's in composition, a mix of nitrogen, oxygen, and some greenhouse gases like carbon dioxide, the global average temperatures could be remarkably moderate, perhaps even similar to a spring day on our own planet. This opens the door to some truly fascinating speculation about its weather and surface conditions. With a thick atmosphere and a rotational period that suggests it might not be tidally locked, this world could experience dynamic weather systems not unlike our own. We can imagine a planet with familiar cloud patterns, where water evaporates from vast alien oceans, condenses into storms, and falls as rain upon strange continents. Prevailing winds might carry weather fronts across its terrain, and the cycle of seasons could unfold as it tilts on its axis throughout its year. The presence of multiple other planets in the system, all orbiting closer to the star, wouldn't significantly affect this world's climate, leaving it as a solitary, stable oasis in its stellar neighborhood. HD 40307G represents a different and perhaps more familiar path to habitability, a world with weather we might recognize, under a sun that feels almost like our own. But our tour of the Proxima Centauri system is not yet complete. While its sibling, Proxima b, captures most of the attention for its potential warmth, a second, more frigid world also orbits this faint star. Proxima Centauri c is a starkly different kind of planet, a super-Earth or mini-Neptune with a mass about 7 times greater than our own world. Its orbit is vastly wider, taking over 5 Earth years to complete a single journey around its dim sun. At this immense distance, the feeble light from Proxima Centauri provides virtually no warmth, plunging the planet into a deep, perpetual freeze where surface temperatures are estimated to be a bone-chilling -234 degrees Celsius. On first inspection, this appears to be a dead world, a frozen wasteland locked in an icy tomb. However, the story of habitability is rarely so simple. The immense mass of Proxima Centauri c suggests it could be a very different kind of world from the rocky Proxima b. Some planetary models indicate it might possess a thick, gaseous envelope, more akin to a small version of Neptune than a large version of Earth. But another, more tantalizing theory proposes that it could be a solid world, a massive rocky or icy super-Earth. If this is the case, its substantial size could generate enough internal heat from the radioactive decay of elements in its core. This internal warmth is a critical factor, as it could maintain a vast, global liquid ocean trapped deep beneath a thick, frozen crust of surface ice. Not unlike the oceans we believe exist on moons like Europa and Enceladus in our own solar system. This possibility opens a door to one of the most exciting ideas in astrobiology: the potential for life in subsurface oceans. Cut off from the energy of its star and protected from the violent stellar flares that batter the system, any ecosystem in such an ocean would be utterly alien. It would be a world of perpetual darkness, where life would have to rely entirely on chemosynthesis, drawing energy from chemical reactions in the seabed, like hydrothermal vents at the bottom of Earth's oceans. We could imagine bizarre, blind creatures navigating the pressurized depths, their forms shaped by an environment we can scarcely comprehend. The very fact that such a world could exist so close to us, a mere 4 light-years away, suggests that these hidden, icy biospheres might be common throughout the galaxy. The stark contrast between the two siblings in the Proxima system is a perfect lesson in the diversity of exoplanets. Proxima b offers the more traditional vision of a habitable world, a planet with the potential for liquid water on its surface, even if its environment is extreme. Proxima c, on the other hand, represents the frontier of the habitable zone concept, pushing us to consider environments we once thought were utterly sterile. It challenges us to expand our definition of life-bearing world, to include those dark, cold realms where heat comes not from a sun, but from the planet's own heart. Together, they illustrate that a single star can host multiple kinds of worlds, each with its own unique story and potential for harboring the chemistry of life. While many of the worlds we've visited orbit stars not too different from our Sun, our journey now takes us to a far more ancient and intriguing stellar family. 1,200 light-years away in the constellation Lyra, the star Kepler-62 has been shining for a remarkable 7 billion years. That's more than 2 billion years older than our own Sun, granting any planets in its system an immense head start in the cosmic race to develop life. And this elderly star is not alone. It is the proud parent of 5 known planets, with 2 in particular standing out as crown jewels in the search for habitable worlds: Kepler-62e and Kepler-62f. The inner of this promising pair, Kepler-62e, is a classic super-Earth, a world about 1.6 times the size of our own. Its orbit places it squarely in the warmer, inner edge of the star's habitable zone, and it completes a full revolution around its aging sun in just 122 days. The sheer amount of stellar energy it soaks up, combined with its significant size, has led many planetary scientists to a compelling conclusion: this world is almost certainly a water world. With a probable thick, steamy atmosphere rich in water vapor and a surface likely devoid of any continents, Kepler-62e could be a planet-wide ocean, a single global sea hundreds of kilometers deep. The pressure at the bottom of such an abyss would be unimaginable, possibly creating an exotic layer of ice that is hot and solid. But in the upper layers where sunlight can penetrate, vast and placid waters could exist. In this eternal ocean, life would have had billions of years to arise and evolve in isolation, potentially giving rise to entirely aquatic ecosystems of breathtaking complexity. Its sibling, Kepler-62f, presents a strikingly different, and perhaps even more tantalizing, vision. This planet is only 40% larger than Earth, making it one of the smallest exoplanets ever found within a habitable zone at the time of its discovery. It orbits much farther out than its sister world, taking 267 days to complete a year and residing in the cooler, outer reaches of the star's life-friendly region. This greater distance from its star, which is itself significantly dimmer than our Sun, means Kepler-62f receives a much gentler level of warming radiation. This opens the door to a fascinating possibility that it could be a world more reminiscent of our own, with a solid rocky surface, exposed land masses, and liquid water oceans. Its cooler location makes a runaway greenhouse effect far less likely, suggesting it could have a stable climate capable of maintaining those essential bodies of liquid water on its surface. The true magic of this system lies in its profound age. 7 billion years is an almost incomprehensible stretch of time, more than half the current age of the entire universe. For comparison, it took life on Earth roughly 1 billion years to emerge, and another 4 billion to evolve to our current technological civilization. The Kepler-62 system has had more than double that entire time span for life to not only begin, but to potentially flourish, evolve, and perhaps even develop intelligence. If life exists on either of these worlds, it has had an eternity to perfect itself, to diversify, and to adapt to its environment in ways we can scarcely imagine. One can wonder if Kepler-62's global ocean is teeming with life forms of stunning diversity, or if the potentially more Earth-like shores of Kepler-62f have been transformed by a civilization that has watched the stars for eons longer than we have existed. These two worlds together offer a masterclass in the variety of habitable environments, proving that a single star can host entirely different kinds of life-bearing planets, each with a story billions of years in the making. Returning to the incredible TRAPPIST-1 system, we now venture beyond the prime candidate of Planet E to explore its fascinating siblings, each a unique world with its own story to tell. The next planet out, TRAPPIST-1f, presents a vision of a world utterly dominated by water. Its density is the lowest among the 7 siblings, a strong clue that a significant portion of its bulk is not rock, but something much lighter. This has led many planetary scientists to conclude that TRAPPIST-1f is almost certainly a water world, a globe completely enveloped by a deep, global ocean that could be hundreds of kilometers deep. Imagine an endless expanse of water under a dull red sun with no land in sight. The sheer pressure at the bottom of this alien sea would be crushing, likely forming a layer of exotic, hot ice that acts as a solid floor. But in the upper layers, where starlight can filter through, this vast ocean could be a perfect incubator for life, an aquatic realm that has been stable for billions of years. Moving further out, we encounter TRAPPIST-1g, the largest of the 7 planets and a true super-Earth. Its greater size and mass give it a powerful advantage in the game of planetary survival, the strong gravity needed to hold onto a substantial atmosphere. This makes it one of the most promising targets for atmospheric study with the James Webb Space Telescope. Early observations suggest it may indeed possess a thick, extended atmosphere, which would be absolutely crucial for regulating its climate. While it receives slightly less energy from its star than Mars does from our Sun, a robust atmosphere rich in greenhouse gases like carbon dioxide could act as a phenomenal insulating blanket, trapping enough heat to raise surface temperatures to levels where liquid water could flow. This world serves as a powerful reminder that a planet's position is not its destiny. With the right atmospheric conditions, a world that seems too cold at first glance could become a temperate oasis. On the frigid outer edge of this remarkable system lies TRAPPIST-1h, the smallest and most distant of the family. Its orbit is so wide that it takes just under 19 Earth days to complete a single year, and it receives a mere trickle of warmth from its cool star. Surface temperatures here are likely well below freezing, making it a frozen world, perhaps similar to the icy moons of our own outer solar system. However, its small size and low density leave an intriguing door open. If TRAPPIST-1h has a composition similar to moons like Jupiter's Europa or Saturn's Enceladus, it could possess a rocky core warmed by the gravitational tug of war with its 6 sibling planets. This internal heat could maintain a liquid water ocean trapped deep beneath a thick, icy crust, creating a hidden, subsurface habitat completely isolated from the cold vacuum above. This means that even the coldest member of this system could potentially host life, not on its surface, but in the dark, warm depth shielded from the harshness of space. Together, these three worlds demonstrate the stunning diversity that can be packed into a single planetary system. TRAPPIST-1F offers the possibility of a global aquatic abyss. TRAPPIST-1G showcases how atmosphere can redefine a world's potential, and TRAPPIST-1H hints at the hidden, warm oceans that might lie beneath a frozen shell. This isn't just a collection of rocks around a star. It's a miniature solar system with a full spectrum of environments, each one a new chapter in the story of how planets form and evolve. The TRAPPIST-1 system, in its entirety, is a gift to astronomy, a nearby laboratory where we can study and compare 7 different Earth-sized worlds, bringing us closer than ever to understanding the true variety of planets the universe has to offer. Amidst the often tempestuous realm of red dwarf stars, our next destination offers a welcome promise of peace. Just 11 light-years away, orbiting a star in the constellation Virgo, is Ross 128b, a world that stands out for one remarkable reason. Its sun is one of the quietest and most stable red dwarfs we have ever discovered. While so many of the stars we've visited are prone to violent, life-scouring flares, Ross 128 is a celestial pacifist. It's an old, inactive star that has settled into a gentle and predictable rhythm, offering its planets a rare and precious gift: billions of years of stellar calm. This planetary tranquility is built upon a foundation of familiar characteristics. Ross 128b is a super-Earth with a mass about 1.35 times that of our own world, placing it firmly in the category of a rocky planet with a solid surface. Its orbit is incredibly tight, completing a full revolution in just under 10 Earth days, but because its star is so dim and cool, this close proximity is exactly what places it within the star's habitable zone. The planet receives only about 38% more stellar radiation than Earth does from our Sun, resulting in an estimated equilibrium temperature that is strikingly similar to our own planet's. This means that, theoretically, with the right atmospheric conditions, its global average temperature could be remarkably temperate. The advantages this world holds over its more chaotic counterparts cannot be overstated. A stable star means a stable climate. Without the constant barrage of high-energy radiation from stellar flares, Ross 128b has a far greater chance of holding onto a protective atmosphere over astronomical timescales. This atmosphere is the key that unlocks its true potential. A blend of nitrogen, carbon dioxide, and water vapor could create a substantial greenhouse effect, effectively trapping the star's faint warmth and distributing it evenly across the globe. This could prevent the planet from becoming tidally locked into extreme hot and cold hemispheres, instead fostering more Earth-like conditions across much of its surface. Visualizing the environment on this world is a captivating exercise. The sky would be dominated by its deep red sun, which would appear larger in the sky than our sun does from Earth, casting a perpetual, dim crimson light across the landscape. Any potential vegetation would have adapted to harvest this specific wavelength of light, possibly appearing in deep shades of black or purple to maximize energy absorption. With a likely thick atmosphere, the sky itself might not be black, but instead a hazy, perpetual dusk glow. The presence of liquid water is a strong possibility, perhaps in vast, still oceans that reflect the burgundy hue of the sky or in rivers carving channels through alien continents. Ross 128b isn't just another exoplanet. It is a testament to the idea that serenity might be one of the most important ingredients for life. A quiet world basking in the gentle light of a peaceful star, offering one of our best chances for finding a truly habitable environment beyond our solar system. Journeying over 800 light-years into the constellation Cygnus, we encounter a world whose discovery was a masterclass in persistence and precision. Kepler 1229b was found not by a single clear signal, but by meticulously analyzing the subtle, complex flicker of its star's light, a signature that initially baffled scientists. This super-Earth, about 1.13 times the size of our own planet, orbits a cool, dim M-type red dwarf star, completing a full revolution every 86.8 Earth days. While that may seem like a short year, its position is perfectly calculated. It resides squarely in the center of its star's habitable zone, receiving just enough stellar energy to place it in that Goldilocks region where liquid water could theoretically exist on its surface. What makes this world particularly compelling is its orbital configuration from our vantage point. The planet transits its star, meaning it passes directly between the star and Earth, causing a tiny, periodic dip in the star's brightness that allows us to detect it. This alignment is a gift for astronomers, as it provides a direct opportunity to study the planet's atmosphere. When starlight filters through the thin, gaseous shell surrounding a transiting planet, it carries with it the chemical fingerprints of the gases present. This makes Kepler 1229b a prime target for the most powerful space telescope ever built. The James Webb Space Telescope is poised to play a transformative role in unraveling the mysteries of this distant world. Its sophisticated instruments are designed to perform detailed spectroscopic analysis on the light that passes through the planet's atmosphere during these transits. Scientists are eagerly awaiting data that could reveal the presence of water vapor, carbon dioxide, methane, or even the tantalizing, potential biosignature of molecular oxygen. The detection of such gases would tell us not just about the planet's climate and composition, but could provide the first hints of biological processes at work on a world hundreds of light years away. The theories about its atmosphere are varied. It could possess a thick, Venus-like shroud that creates a powerful greenhouse effect, or a thinner, Earth-like mix that maintains a more moderate temperature. Its location in the habitable zone suggests the latter is a strong possibility, but only direct observation will provide the answers we seek. Moving beyond the quiet serenity of Ross 128b, we encounter a world that pushes the very definition of habitability to its absolute limit. 36 light-years away, orbiting a star in the constellation Vela, the super-Earth known as HD 85512b challenges scientists with a fundamental question: how much heat is too much? Discovered in 2011, this planet immediately stood out for its precarious position on the inner, scorching edge of its star's habitable zone, a location that makes it one of the most debated and intriguing candidates in our search. With a mass at least 3.6 times that of Earth, HD 85512b is a substantial world, almost certainly boasting a rocky composition and a solid surface. Its powerful gravity would be more than capable of holding onto a substantial atmosphere, a critical factor for its potential. The planet completes a full orbit around its K-type star in a blisteringly fast 58 Earth days, a testament to its incredibly close proximity. This star, an orange dwarf, is notably more stable and less active than the red dwarfs we've frequently visited, offering a more consistent and less hostile radiative environment for any potential atmosphere to persist. The central debate surrounding this world hinges entirely on the nature of that atmosphere and the planet's reflectivity, or albedo. The sheer amount of stellar energy it receives means that for liquid water to exist on its surface, the planet would need a very specific set of conditions to avoid a runaway greenhouse effect that would turn it into a Venus-like hellscape. Sophisticated climate models have explored these scenarios in depth. The most optimistic simulations suggest that if HD 85512b has a surface covered by more than 50% cloud cover, those clouds could reflect a significant amount of the incoming stellar radiation back into space, acting like a planetary sunshade. Coupled with an atmosphere that isn't overly thick with greenhouse gases, this could theoretically keep global temperatures in check. This delicate balancing act makes it a fascinating subject for comparative planetology. When placed next to other super-Earths like the potentially oceanic GJ667cc or the thick atmosphered LHS 1140b, HD 85512b represents the opposite end of the climate control spectrum. Those worlds might struggle to trap enough heat. This one struggles to avoid trapping too much. Its situation is more analogous to a pre-industrial Venus, a planet that might have once been temperate before succumbing to a greenhouse catastrophe. The possibility that it could be a super-Venus is just as strong as the possibility it could be a habitable super-Earth. The ultimate answer lies in the composition of its air, a mystery that next-generation telescopes are poised to solve. The presence of certain chemicals would be a dead giveaway for its nature. If its atmosphere is found to be dominated by carbon dioxide with traces of sulfur dioxide, it would strongly indicate a scorching, high-pressure world. However, if spectroscopy were to ever detect a significant amount of water vapor alongside gases like oxygen, it would revolutionize our understanding of climatic extremes and prove that life can cling to existence in the most unexpected and demanding of corners in the galaxy. HD 85512b serves as a crucial test case for the outer boundaries of the habitable zone, a reminder that the difference between a temperate world and an inferno can be as thin as a layer of clouds. As we push further into the catalog of known exoplanets, we encounter a world that serves as a stark and sobering counterpoint to the Earth-like hopes of many other candidates. 41 light-years from us, orbiting a small red dwarf star in the constellation Vela, is GJ1132b. This planet is not a hopeful sanctuary for life. Instead, it is a fascinating and terrifying window into a planetary apocalypse, a place that may show us the gruesome fate that almost befell our own world. Its claim to fame is monumental. It was the first Earth-sized planet beyond our solar system where we definitively detected an atmosphere. But this is no life-giving blanket of air. It is likely a shroud of toxic fumes, a testament to a world that took a very different evolutionary path. GJ1132b is a rocky world, with a size and mass very similar to Earth's. But any similarity ends there. It orbits so close to its dim star that its year is a mere 1.6 Earth days long. This proximity locks it in a hellish embrace, with surface temperatures estimated to be in the hundreds of degrees Celsius. The planet is almost certainly tidally locked, with one hemisphere permanently scorched by its dull red sun and the other frozen in darkness. For years after its discovery, astronomers assumed it was just another barren, airless rock, its atmosphere long ago stripped away by the intense radiation from its star. But then, the Hubble Space Telescope saw something extraordinary. By observing the star's light as it filtered through the planet's limb during transits, scientists detected the unmistakable signature of an atmosphere. This was a stunning revelation. How could a planet this close to an active red dwarf possibly hold onto its air? The leading theory is as fascinating as it is infernal. The atmosphere we see is not the planet's original one. It is likely a secondary atmosphere, constantly being replenished by massive, planet-wide volcanic activity. The immense gravitational tides from the star, flexing and squeezing the planet's interior, could be heating its core to a molten frenzy, driving endless eruptions that pump vast quantities of gases like hydrogen, methane, and hydrogen cyanide up from below. This makes GJ1132b a potential super-Venus, a world even more extreme than our solar system neighbor. Its surface is probably a global lava field, riddled with fissures and towering volcanoes ceaselessly belching gases into a thick, hazy sky. The atmosphere itself might be divided into layers, with a high-altitude haze of aerosols and hydrocarbons blocking what little light filters down to the surface. This world offers a terrifyingly vivid glimpse into a runaway greenhouse effect in its most advanced stage, a cautionary tale of how a planet can be transformed into an unbearable furnace. Yet, for all its hostility, GJ1132b is a scientific treasure trove. It provides us with a real-time laboratory to study planetary evolution and atmospheric loss under extreme conditions. By studying its air, we learn not just about this specific world, but about the processes that dictate whether a planet becomes a temperate oasis like Earth or a scorched wasteland like Venus. It teaches us that an atmosphere is not a permanent feature, but a dynamic and fragile thing, constantly shaped by the complex interplay between a planet's interior and the relentless fury of its star. This Venus-like world reminds us that the universe is not always built for life, but even in its most hostile corners, it offers profound lessons about our own place in the cosmos. Our final destination on this tour of alien worlds takes us over 1,500 light-years away to a star known as Kepler-283. This orange K-type dwarf is slightly cooler and smaller than our Sun, and it is home to a pair of planets. The outer world, Kepler-283c, stands out as a fascinating and often overlooked candidate in the habitable zone. This super-Earth is about 1.8 times the size of our own planet, placing it firmly in the category of a rocky world with a solid surface and enough gravity to potentially hold onto a life-sustaining atmosphere. Its orbital dance is a key part of its appeal. Kepler-283c completes a full journey around its star in just under 93 Earth days. While that sounds like a short year, its position is perfectly calculated for its specific star. It resides comfortably within the star's habitable zone, that region where temperatures could allow for liquid water to pool on the surface. The amount of stellar energy it receives is about 34% more than what Earth gets from the Sun. This puts it in a slightly warmer category, but far from the scorching extremes of a Venus-like world. With a reflective atmosphere and some cloud cover, its climate could be surprisingly temperate. One of the most captivating possibilities for this world involves the potential for a moon, or even a system of moons. Given its classification as a super-Earth, its stronger gravitational pull makes it an excellent candidate for capturing or holding onto large natural satellites. A sizable moon could provide immense benefits for the stability of any potential biosphere. Just as our moon stabilizes Earth's axial tilt, preventing wild climate swings, a moon around Kepler-283c could offer the same gravitational anchor, ensuring millennia of stable seasons and a consistent climate, a major advantage for the long-term evolution of life. Beyond the potential for moons, the presence of a global ocean is another compelling theory. Its size and position make it an ideal candidate to be a water world, a planet completely enveloped by a deep, planet-wide sea. In such a scenario, the entire surface would be a single, alien ocean, with no landmasses in sight. The depths could be home to hydrothermal vents on the seafloor, acting as oases of chemical energy that could fuel entire ecosystems completely independent of sunlight, much like those found in the darkest parts of Earth's oceans. Despite its promising characteristics, Kepler-283c receives less attention than some of the flashier exoplanet discoveries, largely because it was detected earlier in the Kepler mission's lifespan and is more distant than our nearby neighbors. Yet, its credentials are undeniable. It has the right size, the right orbit, and the right kind of star. It represents the quiet, steady majority of habitable zone worlds, not the closest nor the most Earth-like, but a profoundly important piece of the statistical puzzle, proving that planets with the potential for life are scattered throughout the galaxy, orbiting a diverse array of stars, each waiting for its moment in the cosmic spotlight. But what exactly transforms a distant point of light into a potential haven for life? The concept is far more nuanced than simply finding a planet at the right distance from its star. The science of habitability is a delicate balancing act, a cosmic checklist of conditions that must align to create an environment where chemistry can blossom into biology. At the heart of this search is the famed Goldilocks zone, or the habitable zone, that region around a star where temperatures are just right, not too hot and not too cold, or liquid water to exist on a planetary surface. This isn't a fixed distance, it's a shifting belt of orbital real estate entirely dependent on the star itself. A blazing hot, massive star has a habitable zone that is incredibly wide and very far out, while a cool, diminutive red dwarf like TRAPPIST-1 has a narrow habitable zone so close in that its planets have years shorter than a month on Earth. This is why we find so many promising worlds orbiting these faint, red suns. Their habitable zones are easier to scan, and their small size makes the telltale dip of a transiting planet easier to spot. The type of star is perhaps the single most important factor dictating a planet's potential. Our own steady, benevolent G-type sun is something of a cosmic rarity. The most common stars in the galaxy are M-dwarf red dwarfs, and they present a double-edged sword. They are long-lived, shining for trillions of years, which offers life an unimaginably long timeline to emerge and evolve. However, they are also often tempestuous, prone to violent flares that can bombard their closely orbiting planets with lethal doses of X-ray and ultraviolet radiation, threatening to strip away any atmosphere and sterilize the surface. This is the great challenge for planets like Proxima Centauri b. In contrast, older, quieter red dwarfs like the one hosting Ross 128b offer a much more stable and promising environment, proving that not all small stars are created equal. Orange K-type dwarfs, like the one hosting HD 40307g, are considered Goldilocks stars by many astronomers. They are more stable and longer-lived than Sun-like stars, but less volatile than most red dwarfs, offering a peaceful and persistent light for billions of years. A planet's mass is its foundational attribute, determining its very nature and its ability to hold onto the ingredients for life. Too small, like Mars, and its gravity is too weak to retain a substantial atmosphere or maintain internal heat to drive geological activity. Too large, and you cross the threshold into a mini Neptune, a world with a massive, gaseous hydrogen-helium envelope and crushing pressures, with no solid surface to speak of. The sweet spot lies with rocky planets and super-Earths, like LHS 1140b and Kepler 1649c. Their substantial mass provides the gravity necessary to anchor a life-sustaining atmosphere, acting as a shield against stellar radiation and a blanket to trap heat. This mass also likely powers a molten core, which in turn could generate a protective magnetic field. This invisible force field is a planet's first line of defense, deflecting the star's damaging charged particles and preventing them from slowly eroding the atmosphere away into space, a fate that likely befell Mars. This leads us to the critical role of the atmosphere itself, which is the ultimate climate control system for any world. An atmosphere does far more than just provide air to breathe. It regulates temperature, distributes heat, and creates pressure that allows water to remain liquid. The composition of this atmospheric blanket is everything. A thin, wispy atmosphere like that on Mars cannot retain heat, leaving the planet frozen. A too thick atmosphere, dominated by greenhouse gases like carbon dioxide as on Venus, creates a runaway greenhouse effect, turning the planet into a scorching oven. The right mix, as on Earth, can create a temperate global climate. This is why the James Webb Space Telescope is so focused on atmospheric spectroscopy. By analyzing the starlight that filters through an exoplanet's air, we can decipher its chemical composition. Finding a combination of gases that are out of chemical equilibrium, like both oxygen and methane, could be a powerful hint of biological activity, as life is constantly disturbing the atmospheric balance. Two other fascinating physical forces sculpt these alien environments: tidal locking and the greenhouse effect. Tidal locking, a likely reality for many planets orbiting red dwarfs, occurs when a planet's rotation period matches its orbital period, forcing one hemisphere to forever face the star while the other is locked in perpetual night. This creates a world of extreme contrasts, with a scorching hot day side and a brutally cold night side. The potential for life then hinges on whether the planet's atmosphere is thick enough to efficiently transport heat from the day to the night hemisphere. carving out a temperate twilight zone along the Terminator line where conditions might be just right. The greenhouse effect, often villainized on Earth, is an essential planetary service in moderation. Gases like carbon dioxide, water vapor, and methane in a planet's atmosphere allow sunlight to pass through but trap the infrared heat that radiates back from the surface. This is what keeps Earth from being an ice ball. For a planet like TRAPPIST-1G, which receives little energy from its star, a strong greenhouse effect powered by a thick atmosphere could be the very thing that raises its temperatures to a hospitable level, turning a frozen world into a watery one. It is the intricate and dynamic interplay of all these factors: a stable star, a rocky planet of the right mass, a protective magnetic field, a life-giving atmosphere, and orbital dynamics that conspires to turn a barren rock into a living world. But how do we even know these remarkable worlds exist? After all, they are impossibly distant pinpricks of light, lost in the glare of their far brighter stars. The methods astronomers use to find them are feats of ingenuity, allowing us to deduce the presence of a planet from the subtlest of clues. The most prolific technique, responsible for thousands of discoveries, is transit photometry. Imagine a tiny moth flying across a brilliant spotlight far away. You wouldn't see the moth, but you would notice the light very slightly dim. This is precisely how telescopes like Kepler and TESS operate. They stare unblinkingly at fields of stars, meticulously measuring their brightness. When a planet crosses in front of its star from our line of sight, it causes a tiny, periodic dip in that star's light. The depth of the dip tells us the planet's size relative to its star, and the timing tells us the length of its year. This method also gifts us our best chance at detecting atmospheres, as starlight filtering through that thin gaseous shell carries the chemical fingerprints of the gases within, ready for the James Webb Space Telescope to decode. Another powerful technique, radial velocity, measures the gravitational tug of war between a planet and its star. A star is not a fixed anchor. A planet's gravity causes the star to wobble in a tiny, delicate dance. As the star moves ever so slightly towards us, its light is compressed, shifting slightly towards the blue end of the spectrum. As it wobbles away, the light stretches, shifting towards red. By detecting these rhythmic blue shifts and red shifts in a star's light, astronomers can infer the presence of an orbiting world. This method is exceptional for telling us a planet's mass and orbital period, but it doesn't require the planet to pass in front of the star from our view, allowing us to find worlds in a wider range of orbital inclinations. When combined with the transit method, these two techniques provide a stunningly complete picture, revealing a planet's density and therefore its likely composition, whether it is a gaseous mini-Neptune or a solid, rocky super-Earth. For the most dramatic and visually stunning discoveries, we turn to direct imaging, the Herculean task of actually taking a picture of an exoplanet. This is an incredible technical challenge, like trying to photograph a firefly hovering next to a massive searchlight from thousands of miles away. To achieve this, astronomers use advanced instruments called coronagraphs or star shades, which are designed to physically block the overwhelming glare of the host star, allowing the faint, reflected light of the orbiting planet to be detected. This method works best for young, hot, giant planets on very wide orbits, worlds that are still glowing with the heat of their formation and are far enough from their star to be distinguished. While it has revealed only a handful of planets so far, these direct images are profound, providing actual snapshots of alien solar systems in their infancy and giving us a glimpse of what future interstellar explorers might one day see. The future of this search is even more breathtaking, with a new generation of missions poised to revolutionize our understanding. The European Space Agency's Plato mission, scheduled for launch in 2026, is designed to be a planetary transit hunter on an unprecedented scale. Its array of 26 powerful cameras will monitor hundreds of thousands of bright stars, seeking out Earth-sized planets orbiting in the habitable zones of Sun-like stars. Plateau precision will allow it to not just find these worlds, but to perform seismic analysis on their host stars, determining the star's exact age, mass, and radius with extraordinary accuracy. This, in turn, will tell us the precise size and age of the planets themselves, moving us from simple discovery into the realm of detailed characterization on a massive scale. Looking further ahead, concepts like the NASA-led LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, represent the next great leap. Envisioned as a giant, flexible observatory with a mirror potentially 15 meters across, dwarfing the James Webb Space Telescope, LUVOIR would be powerful enough to directly image and analyze the atmospheres of dozens of Earth-like exoplanets. It could search for a range of biosignatures, from oxygen and ozone to the telltale red edge of vegetation, providing statistical evidence for how common life might be in our galaxy. These future missions will transform the points of light we study today into richly detailed worlds, each with its own climate, weather, and perhaps even the unmistakable signs of a living biosphere, bringing us closer than ever to answering the timeless question of whether we are alone in the universe. To truly appreciate the potential for life on these alien worlds, we must first look no further than our own planet, a place teeming with organisms that thrive in conditions we once believed were utterly incompatible with life. These incredible life forms, known as extremophiles, are not merely surviving on the fringes. They are flourishing in some of the most hostile environments Earth has to offer, completely redefining our understanding of where life can take root. From the crushing, sunless depths of the ocean floor to the acidic, boiling waters of hot springs, extremophiles demonstrate a breathtaking resilience that gives us profound hope for discovering biology beyond Earth. Consider the astonishing ecosystems clustered around deep-sea hydrothermal vents. These are geological features on the ocean floor where superheated water, rich in minerals, spews from the Earth's crust into the freezing darkness above. No sunlight penetrates these abyssal plains, which means photosynthesis, the foundation of nearly every ecosystem on the surface, is impossible. Yet, these vents are oases of life. Giant tube worms, bizarre blind crabs, and unique species of shrimp thrive here, not by harnessing the sun's energy, but through chemosynthesis. Specialized bacteria form the base of this food web, converting the toxic hydrogen sulfide and other chemicals from the vent fluid into usable energy. This entire complex community exists in perpetual darkness, under pressures that would instantly crush a human, surrounded by water that would scald any surface creature. If life can build such vibrant communities completely independent of sunlight in the most inaccessible parts of our own world, then the subsurface oceans of icy moons like Europa or Enceladus, or a water world like K218b, suddenly seem like prime real estate for biology. The lessons from Earth's extremes extend far beyond the deep sea. In the bone-dry valleys of Antarctica, one of the driest and coldest deserts on the planet, life persists in the porous spaces within rocks. Endolithic microbes find a precarious refuge just millimeters beneath the stone's surface, protected from the deadly ultraviolet radiation and extreme cold, harvesting minute amounts of moisture from the air and performing photosynthesis with the faint light that penetrates their rocky shell. In the hyper-acidic, metal-rich rivers winding away from mines, other extremophiles flourish, their cellular machinery perfectly adapted to an environment that would dissolve most other life. These organisms don't just tolerate acid, they require it. These terrestrial examples provide a powerful toolkit for interpreting the potential habitability of the extreme exoplanets we are discovering. A tidally locked world like Proxima Centauri b, with its eternal day and night sides, no longer seems like an automatic death sentence. We can envision hardy, radiation-resistant microbes clinging to existence in the temperate terminator zone, much like the endolithic organisms in Antarctic rocks. The thick, hydrogen-rich atmosphere of a Hycean world like K218b might be toxic to us, but it could be the perfect blanket for an entirely different form of biochemistry, perhaps one based on liquid hydrocarbons or other solvents instead of water. Life might not use DNA as its genetic blueprint. It could employ a completely different molecule capable of withstanding immense pressures or exotic chemistries. The possibilities are as vast as the universe itself. The discovery of extremophiles has taught us that life is not a delicate, rare phenomenon that requires a perfect, Earth-like balance. Instead, it appears to be a tenacious force, an inevitable consequence of chemistry wherever the right ingredients and conditions persist, no matter how alien those conditions may seem to us. This fundamental shift in perspective turns every single one of the 25 worlds we've explored from a mere point of data into a canvas for our imagination, a place where the enduring ingenuity of life might have found a way. For decades, discovering an exoplanet was like spotting a distant ship on the horizon. We knew it was there, but its true nature remained a mystery. We could determine its size, mass, and orbit, but the crucial details of its atmosphere and surface were locked away, invisible to our instruments. This all changed with the advent of a new era in astronomy, spearheaded by the most powerful space observatory ever built, the James Webb Space Telescope. Unlike its predecessors, which primarily discovered planets, JWST is designed to intimately know them, to dissect the very air they breathe and search for the chemical whispers of life itself. The telescope's revolutionary power lies in a technique called transmission spectroscopy. When a planet transits or passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Every gas in that atmosphere absorbs light at specific, unique wavelengths, like a chemical fingerprint. JWST incredibly sensitive infrared instruments are built to catch this filtered starlight and spread it out into a spectrum, a barcode of absorption lines that reveals the atmosphere's exact composition. It's like turning a faint, blurry dot into a detailed weather report from light years away, telling us about temperatures, clouds, and most importantly, the presence of potential biosignatures. A biosignature is not a single magic bullet gas. It's a combination of chemicals that are hard to explain without the presence of biology. On Earth, the simultaneous presence of large amounts of oxygen and methane is a classic example. These gases react with each other and quickly disappear from the atmosphere unless they are constantly replenished. On our planet, life is that engine photosynthesizing organisms pump out oxygen, while microbes and animals produce methane. Finding a similar unstable combination in an exoplanet, its atmosphere would be one of the strongest hints we've ever had that we are not alone. This is precisely why a world like K218b became an overnight celebrity in astronomy. Earlier observations by the Hubble Space Telescope had detected water vapor in its hydrogen-rich atmosphere, but JWST was able to look far deeper, confirming the water and revealing the presence of carbon dioxide and methane. This specific mix of gases is incredibly intriguing for a potential Haitian world, a planet with a vast global ocean beneath a thick atmosphere. Most tantalizing of all, the data contained a tentative signal for dimethyl sulfide, a molecule that on Earth is produced almost exclusively by marine phytoplankton. While this detection is not yet confirmed and requires further observations, it showcases the breathtaking precision of JWST. We are no longer just guessing about habitability. We are beginning to inventory the building blocks of life in alien skies. Yet JWST does not work alone. It is part of a powerful fleet of observatories, both in space and on the ground, that are collaborating to paint a complete picture. Large ground-based telescopes like the extremely large telescope in Chile, once completed, will use a technique called high-contrast imaging to directly photograph Jupiter-sized exoplanets, complementing JWST transit studies. The now retired Spitzer and Hubble telescopes laid the essential groundwork. And future missions like the European Space Agency's RIEL mission are designed specifically to conduct large-scale surveys of exoplanet atmospheres, acting as a census taker to identify the most promising targets for JWST detailed follow-up investigations. The ultimate goal of this grand observational campaign is to move from detecting individual gases to understanding entire atmospheric systems. We want to know not just what is in the air, but how it behaves. Does the atmosphere circulate heat efficiently, moderating the extremes of a tidally locked world? Does it have protective layers that shield the surface from harmful radiation? Are there seasonal variations in its composition that might hint at biological cycles? Each planet we examine adds a new data point, helping us create a more nuanced scale of habitability that goes far beyond the simple concept of the Goldilocks zone. With every observation, JWST and its partners are transforming exoplanet science from a discipline of discovery into one of true exploration, bringing us closer than ever to answering the profound question of whether the cosmic recipe for life has been followed elsewhere. Of course, all this incredible progress brings with it a host of profound challenges and controversies that scientists are grappling with every single day. One of the biggest debates starts with the very definition of the word we've been using all along: habitability. Our entire search is fundamentally biased by a single data point: life on Earth. We search for liquid water, Earth-like temperatures, and atmospheres with gases like oxygen, because that's what we know works. But what if we're suffering from a severe case of planetary chauvinism? Life elsewhere could be based on an entirely different biochemistry, perhaps using liquid methane as a solvent on a frigid world like Saturn's moon Titan, or thriving in the supercritical fluids beneath the ice shells of distant moons. By focusing our search so narrowly on what we call the habitable zone, we might be blind to entire categories of life that exist in environments we currently consider utterly hostile. The universe is under no obligation to cater to our expectations, and the most alien life forms might be the ones we're not even looking for. This leads directly into one of the most treacherous aspects of the search: the problem of false positives in biosignature detection. Imagine the moment astronomers announce they've found oxygen and methane in the atmosphere of a distant world. The headlines would understandably explode with the news that we've found life. But the scientific community would be far more cautious, because nature has many ways to mimic the signs of biology. Oxygen, which we produce through photosynthesis, can also build up abiotically through the breakdown of water molecules by intense stellar ultraviolet radiation. Methane can be belched out by volcanoes and geothermal activity on a completely sterile world. A planet might show all the right atmospheric signs and still be utterly barren, its chemistry fooling our telescopes from across the galaxy. This is why scientists are desperately working to identify technosignatures, or signs of technology, which would be harder to fake, but even those come with their own set of ambiguities. The journey from a promising signal to a confirmed discovery of life will be a long one, filled with rigorous debate and the painstaking process of ruling out every possible non-biological explanation. Perhaps the most weighty and philosophical controversy of all involves the ethical considerations of contact. If we were to discover an unmistakable technosignature, a signal of intelligence, what do we do next? The debate between active and passive SETI, the search for extraterrestrial intelligence, is fierce. On one side are those who advocate for active SETI, or METI, messaging extraterrestrial intelligence. They argue that we should be proactive, broadcasting powerful, targeted messages to promising star systems to announce our presence and express a desire for conversation. They see it as a hopeful, open-handed gesture. On the other side are cautionary voices like the late Stephen Hawking, who warned that broadcasting our location to the cosmos could be incredibly dangerous. He compared it to the arrival of Europeans in the Americas, which did not turn out well for the native populations. An advanced civilization capable of interstellar travel might not see us as equals, but as a resource, or simply as pests to be eradicated. The stakes couldn't be higher. It's a decision that could affect the entire future of humanity, and there is no global consensus on who even has the right to make that call. Is it a decision for scientists, for governments, or for all of humankind? These controversies aren't roadblocks. They are essential parts of the scientific process, forcing us to think more deeply and prepare more thoroughly. They push us to refine our instruments, to question our assumptions, and to consider the profound responsibility that comes with this great search. It's a reminder that the quest to find alien life is about far more than astronomy and biology. It's a project that forces us to look in the mirror and ask fundamental questions about who we are, what we value, and what kind of future we want to create, both for ourselves and for any neighbors we might one day meet among the stars. And so our incredible journey across 25 light years and countless possibilities draws to a close. We've stood on the potential shores of Proxima Centauri b, imagining its vast twilight zone. We've marveled at the compact family of 7 Earth-sized worlds orbiting TRAPPIST-1, each a unique experiment in planetary formation. We've considered the global ocean that might cover K2-18b, and pondered the ancient, potentially life-seeded systems of Kepler-62. From the crushing pressure of super-Earths like LHS 1140b to the delicate climatic balance of HD 85512b, we've explored a staggering diversity of worlds that push the very definition of habitability to its limits. Each of these 25 alien worlds, from our closest neighbor to those over 1,500 light-years away, represents a profound question mark, a story waiting to be read in the faint light of distant suns. This grand tour does more than just catalog exotic planets. It holds up a mirror to humanity and forces us to confront our place in the cosmos. For millennia, we gazed at the stars and wondered if we were alone, a singular spark of consciousness in a vast and silent universe. Today, the evidence points overwhelmingly toward a galaxy brimming with real estate that could host life. The sheer number of these worlds, let alone the thousands more we've discovered, suggests that Earth is not a unique miracle, but perhaps a common outcome of cosmic evolution. We are likely not the center of the universe, but we are something perhaps even more remarkable. We are the universe becoming aware of itself. We are the part of the cosmos that has developed the curiosity and the technology to look out, to ask these questions, and to begin the painstaking work of searching for our cosmic neighbors. This search humbles us, but it also connects us to something magnificent. We are all literally made of stardust, on a tiny rock orbiting an average star, trying to find our family. The adventure, however, is just beginning. Every answer we find unlocks a dozen new questions. The James Webb Space Telescope is right now analyzing the atmospheres of these worlds, and future missions like Plato and the concept for LUVOIR promise to bring even more distant planets into breathtaking focus. The greatest discovery in human history might be just one observation away. This isn't a story for scientists alone. It's a human story, a shared narrative of exploration that belongs to all of us. Every time we look up at the night sky, we are participating in that story. Now we want to hear from you. After this tour of potential alien homes, which exoplanet captured your imagination the most? Was it the tidally locked drama of Wolf 1061c, the serene stability of Ross 128b, or the watery mystery of TOI 700d? Share your favorite in the comments below, and tell us why you think it's the best candidate for life. The conversation is a crucial part of the journey. If you enjoyed this voyage to the frontiers of science and want to join us on the next one, make sure to hit that subscribe button and ring the notification bell. We're constantly exploring the deepest mysteries of the cosmos, from the potential for life on Mars to the mind-bending physics of black holes. and we don't want you to miss a single discovery. Thank you for embarking on this expedition across the stars. Keep looking up, keep wondering, and never lose that sense of awe for the incredible universe we call